Okay, so let's start the analysis by looking at a very simple case first, because DFDU is something that sounds very complicated, right? So let's actually look at linear scalar ODEs. We look at du over dt just equal to lambda times u. Very simple. So lambda is a given constant, right? So last week we tried lambda equal to -1, right? When we are trying the 3 different solvers, and that's when we found that forward order actually worked best. The midpoint rule, which was second order, worked okay, except for when you perform a long time integration, you start to getting oscillations. And the fourth order scheme is unusable, just a period. So let's look at, for a general lambda, how our previous error formula looked like. All right. So we'll do this both for forward order and the midpoint rule. So you get a general idea of how to analyze if a particular scheme is a good choice for solving a particular equation. Okay, so let's do that. Here, if we use forward order, let's use what color do you want for let's do black for forward order. It's kind of the most boring scheme out there. So you have u at time step n. So here, let's actually, because we are doing error analysis, let's be careful with our notation. Let's actually denote u hat of n as our numerical solution. Minus u hat of n divided by delta t would be equal to lambda times u hat of n, right? If you choose to substitute the analytical solution into the same equation, you wouldn't get equal anymore. You would get an approximately equal, right? You would get, sorry, everything should be u. You get approximately equal to lambda times un. And can we be a little bit more quantitative? What is this approximately equal? How do you quantify this approximately equal?
Plus the error.
Plus the error, that's right. And how much error, if we write it to be equal plus an error term, how much error do we have?
Order.
Yeah, order, that's a very good word. So when we write the error term, it's very good to write it as an order of some small quantity that you can control, right? In this case, we can control delta t. That's our choice. So for forward order, that's order what? Delta t. Yes, that's a first order scheme. That's actually through Taylor series analysis. Again, that's how accurate this guy is approximating the du dt, right? And du dt according to our differential equation. If u is the analytical solution, then du dt is exactly equal to lambda times u, right? So if we use the numerical solution, then this is only approximately equal. But because u here is analytical, this is exactly equal. Okay. So these two equations, one numerical, one analytical, is going to give us the equation of solution error, right? Not the error in approximating the derivative, but the error in actually using this formula to integrate an ODE. So by subtracting them, if we define E of n to be defined as u hat of n divided by un, then this formula gives us E of n plus 1. Just by subtracting the first equation from the second equation from the first one, we get equal to lambda times E of n plus O delta t, right? Okay, now we are going back to the more general case we had on the last slide, that is E of n plus 1 would be equal to, oh sorry, this is E, I'm always En plus multiply delta t on both sides, lambda times delta t, En plus O what? We get one more order, right? Delta t squared. All right. So we get one more order that is going to be removed when we actually look at the global order of accuracy, because we are repeating this formula for many times. Okay, so now we are getting back to the question of is the scheme a good or not? And we know a scheme is good if it's accurate and stable. So the question is here, is the scheme stable? If I have some error term that it keeps being added to the equation, will that error term be accumulated or damped out?
Accumulated.
It's going to be accumulated, but like okay. So let me write it a little bit more. So we have two terms, that is lambda times delta t. That is e to the n. So we combine both terms into this, and then we have O delta t squared, right? Now this is the multiplier. I mean that's going to be multiplied because this is 1 plus delta t times, if you substitute the same formula, we have 1 plus lambda delta t times e to the n minus 1 plus O delta t squared, n plus O delta t squared, right? That's just the substituting the same equation recursively. And I can say dot dot dot, it is equal to 1 plus lambda delta t to the what? To the n plus 1th power times e0, right? Okay, plus 1 plus lambda delta t to the nth power times the first time this O delta t squared is added, right? And then plus 1 plus lambda delta t n minus 1th power also times this one, plus dot dot dot, and at the end we have just the O delta t squared term. So we have this many O delta t squared term added together. Each one is multiplied by a certain power of 1 plus lambda delta t. So now we have a good idea of what we want this thing inside the power to be. Again, the magnitude has to be less than 1, right? In previously, in the last lecture, we studied the so-called zero stability. That is a special case of this when lambda is equal to 0, right? We're integrating du dt equal to 0, and we want to analyze, is the scheme capable of integrating the simplest ODE in the world? And it turns out our fourth order scheme is not even able to do that. So now we are getting to no longer the simplest equation in the world, but still pretty simple equation, du dt equal to lambda t. And this lambda actually multiplied with delta t is going to determine if the scheme is going to amplify this error or is going to decay this error, right? And it's the decay that we want.